This topic is measurement techniques, but it contains many fundamentals. So it takes more time to complete this lecture. Okay, let me start. Tracking the individual threat. Radon detection techniques for health and safety. As repeated in visual and odorless, radon is a radioactive gas that cannot be detected without specialized measurement techniques. Health risks. Long-term exposure to elevated radon levels is the second leading cause of lung cancer. Regional variability. Radon levels can vary significantly by location, so measuring radon is crucial to assessing and mitigating risks in different areas. Effective mitigation requires accurate detection. Only through precious radon measurement can effective mitigation strategies be implemented to reduce exposure. Public awareness and safety. Radon measurement techniques are key to raising awareness about radon risks through accurate data. I'll show you the unit definitions or quantities. The historical units we have historical units of exposure. In the United States, they use picocurie per liter. This is old unit. 1 picocurie per liter equals 37 becquerel per cubic meter. Here is a special unit, working level. 1 working level represents many combinations of short-lived radon decay products in 1 liter of air that will result in the ultimate emissions of 1.3 times 10 to 5th MeV of potential alpha energy. Working level mass, WLM, referring to exposure to 1 working level for a working month of 170 hours. This unit, working level month, is commonly used in uranium mines for radiological protection. Here's the activity. The number Tm of spontaneous nuclear transition or nuclear disintegration of a radionuclides of amount N produced during a short time interval dt. The unit activity is becquerel. The activity concentration. Activity A per unit volume V of the respective isotope. The unit of activity concentration is becquerel per cubic meter. Potential alpha energy, PAE, the potential alpha energy of a single atom of a short-lived radon progeny radionuclide is the total alpha energy emitted during the decay of this atom, but not including the relatively long-lived radionuclides led to 10. Here is the potential alpha energy derived from polonium-218. The potential alpha energy is a quantity of characterizing radon progeny atmospheres, not radon atmospheres. It can be written by this equation. This is atom concentration. Here's the energy. N is the number of respective atoms used for theoretical work. The unit potential alpha energy is Joule. Potential alpha energy concentration, PAEC. The potential alpha energy concentration of any mixture of short-lived radon daughters in air is the sum of the potential alpha energy of all short-lived daughter atoms present per unit volume of air. PAEC can be written like this. This is activity concentration. This unit, PAEC expressed in joule per cubic meter or MeV per liter, and working level. One working level equals 1.3 times 10 to the 5th MeV per liter, which is equivalent to 2.08 times 10 to minus 5th joule per cubic meter. So here is a practice. Convert one working level to potential alpha energy concentration for radon progeny, PAEC expressed in MeV per liter and joule per cubic meter respectively. Note that the following information will be available accordingly. Okay, this is a practice, but you see, you can find the answer here. But I suggest you should calculate PAEC independently. Exposure to radon, the time integral of the activity concentration during the defined period of time is a time integrated concentration. The unit of exposure to radon is becquerel per cubic meter hour. Potential alpha energy exposure, the time integral of the potential alpha energy concentration in air Cp over a given time period, delta T. The unit of potential alpha energy exposure is joule per cubic meter hour. Regarding equilibrium factor, in practice, radon and its progeny will rarely be in equilibrium. Equilibrium factor characterizes the disequilibrium between radon gas and its progeny. The equilibrium factor can vary from 0 to 1. There is a negative correlation between equilibrium factor and ventilation rate. For example, indoor environment, equilibrium factor is around 0.4 by natural ventilation. In mines, equilibrium factor is about 0.2 by forced ventilation. This is a sample of individual concentrations of radon and radon progeny. Look at this. So we use equivalent concentration, EEC, very often. EEC, equilibrium equivalent concentration, is an alternative to using PAEC. Equilibrium equivalent concentration is the concentration of radon in equilibrium with its progeny that would give the same PAEC as the actual non-equilibrium mixture. If the radon concentration is known, the EEC can be estimated like this way. This EEC equals concentration of radon times equilibrium factor. If the concentration of the individual radon decay product is known, the following equation can be used to determine the EEC. Look at this. So there is this practice. Air contains the following radionuclides: radon concentration 70 becquerel per cubic meter, unattached radon progeny concentration 10 becquerel per cubic meter, 3 becquerel per cubic meter, and 1 becquerel per cubic meter. Attached radon progeny concentrations is 40 becquerel per cubic meter, 25 becquerel per cubic meter, and 15 becquerel per cubic meter. What are the equivalent radon concentration? EERC, unattached fraction, FP, and equilibrium factor. Before this working on the practice, I have to explain the attached fraction and unattached fraction. Attached fraction, after radon solid progeny generation, radioactive aerosols are formed in two steps: unattached fraction and attached fraction. Look at this. The sum of attached and unattached fractions is equal to 1. The fraction of the potential alpha energy concentration of short-lived radon progeny that is attached to the ambient aerosol particles. So nucleation mode particle activity median diameter varies between 10 and 100 nanometers. Accumulation modes AMD varies between 100 and 450 nanometers, and cosmode particles AMD more than 1 microns. This is micron. Unattached fraction, Fp. A fraction of progeny may not become attached to ambient particles, and its quantity is often referred to as the free and unattached fraction. The unattached fraction is defined as a fraction of the potential alpha energy concentrations of short-lived radon progeny that is not attached to the ambient aerosol. Calculated using the following equation. Fp equals unattached EEC over total EEC. The range of unattached fraction is observed 0.05 to 0.15 without aerosol sources, less than 0.05 with aerosol sources such as smoking, cooking, and stove heating. Then, okay. So once again, air contains the following radionuclides: radon concentration 70, and attached radon progeny concentrations: polonium-218, lead-214, bismuth-214, 10, 3, and 1. Attached radon progeny concentrations: polonium-218, lead-214, bismuth-214, 40, 25, and 15. Then we will calculate the equilibrium radon concentrations and unattached fraction and equilibrium factor. You can see EERC 0.116 times this unattached polonium-218 activity concentration plus 40. This is attached polonium-218 activity concentration. And here, this is unattached and attached. For here is a lead-214, and bismuth-214 is here. One is unattached and attached. Then we obtained 25.76 becquerel per cubic meter. Then, in the case of unattached fraction, we can calculate like this way. This is total EERC. And here is unattached EERC. 10, 3, and 1. Then, unattached fraction was 0.116. After that, we can calculate equilibrium factor. We can calculate like this way: 25.76 over 70. The result is 0.368. 。 . 。  . 。 。 . 。 . 。 . 。 . 。 。 . 。 。 . 。 。 . 。 。 . 。 。 。 。 。 . 。 。 。 . 。 。 。 。 。 . 。 。 。 。 。 。 。 。 。 。 . 。 。 . 。
「
measurement techniques. Classification of detection. Detection methods, direct method, and indirect method. Alpha particle detection, a scintillation detector, gas field detector, solid state nuclear track detector. Alpha detection, semiconductor detector, solid state track detector, nuclear track detector, beta particle detection, scintillation detector, gamma ray detection, semiconductor detector, and scintillation detector. Here are objectives of measurement. Long-term indoor and wait a moment. Sorry. Long-term indoor radon and radon progeny assessment. Short-lived indoor radon screening. Identifying success or failure of preventive remedial measures. Those assessments based on radon and its progeny concentrations. Risk communication. Epidemiological investigations of the health impact of radon exposure, and scientific research. Classification of time resolution, graph sampling technique. The radioactive contents of discrete samples of an air taken over a short term at a single point is analyzed. In the case of continuous technique, this technique is designed to provide information on the time dependence of concentrations. In the case of integrating technique, it provides a single concentration determination, generally averaged over a period of a few days to a year. I can show you the international standard of radon methodology. ISO provides radon standardized technique methodology on radon 11665. This, for example, the measurement of decay products, ISO provides two standards on ISO 116652 contains of integrated measurement techniques. ISO 11665 Part 3 gives a spot measurement. In other words, this is a graph sampling, small intermittent measurement. In the case of radon, Part 4 gives an integrated measurement. Part 5, continuous measurement. Part 6, spot measurement. Here's the application. Part 7 provides accumulation method for estimating surface acceleration rate. Part 8, methodologies for initial and additional investigations in buildings. Part 9 gives test methods for acceleration rate of building materials. Part 11, test methods for soil gas with sampling at depths. Here's the classification of collection method. Collection method of radon gas is classified into two methods. One is passive method. No power supply, integral exposure experiment. This technique is suitable for integral exposure measurement. This technique needs analysis after exposure using special equipment, track edge, activated charcoal, and electrolyte. In the case of active devices, active methods, electric power required. Wait a moment. Thank you for waiting. Electric power, in the case of active devices, electric power is required. It can store the time distribution of radon concentration. And we can get the direct data. For instance, silicon detector with high voltage chamber and alpha spectroscopy, ionization chamber, and scintillation cell. Here is an example of active devices. This device is based on the electrostatic collection method. This is commonly used alpha gun based on pulse type ionization chamber. There are many types of radon monitors. Ionization chamber, ionizing energy of air about 34 electron volts per charge carrier. One alpha with 3.5 MeV energy result in about 10 to 5th charge carriers. In other words, ion pairs. Ionization chamber is well known and recognized as a standard equipment in order to calibrate other detectors. This ionization chamber is used as a primary device. As their characteristics, the volume, inner volume is 1 to 15. Someone raising a hand.
Hello, Supriya ma'am.
Hello?
Hello, Supriya ma'am. If there is any question from your side. Sir, you may continue, sir.
Okay. Thanks. The inner volume is generally 1 to 1.5 liter, made of stainless steel. The larger the volume, the higher the sensitivity. If you choose a larger volume, you can get high sensitivity. So here is a commercial product of ionization chamber, namely alpha-GAD. Alpha-GAD uses a pulse ionization chamber filled with an ambient air. Here's alpha-GAD. Alpha particles produce many ion pairs as they move through the gas, with the number of pairs being proportional to the energy lost by the alpha particles. Signals the primary alpha decay of radon plus subsequent polonium-218 decay. Got this. Here's a electrolyte, and outer gas, outside air go through, enter the chamber through the fiberglass filter. This device can select airflow mode and diffusion mode. Measurable range is 2 to 2 million becquerel per cubic meter. Minimum detectable level is less than 2 becquerel per cubic meter. Efficiency 1 ppm at 20 becquerel per cubic meter. Diffusion and flow mode. We can choose the diffusion mode and flow mode. And this monitor also can measure the relative humidity, temperature, and atmospheric pressure. As a drawback, background from polonium-210 increases over the lifetime of the instrument. This is another type of ionization chamber, namely Atmos, made in Sweden. The principle, 2.2 liter pulse height chamber. Measurable range 1 to 10,000. 100,000 becquerel per cubic meter. Measurement precision 10% at 800 becquerel per cubic meter and measuring time. Minimum detectable activity 5 seconds at 1,800 becquerel per cubic meter. 1 minute at 150 becquerel per cubic meter. 1 hour at 2 becquerel per cubic meter. Air humidity above 10 grams per cubic meter can affect the measurement result. Regarding scintillation cell, it is most useful device for radon measurement. Therefore, it is used as a secondary device. It is often called Lucas chamber, Lucas cell. As their characteristics, the inner volume is 100 to 300 milliliter. Easy to handle, and the inner wall is painted with zinc sulfide scintillator. But energy discrimination is not possible. The typical counting efficiency is estimated to be 75 to 80%. Here is a commercial product of scintillation cell, Pylon 600A and AB7. This is a counting device. AB7 characteristics, active and passive scintillation cells are available. Maximum counting rate to 10,000 CPS. Electronic background less than 0.4 CPM. Pylon 600A characteristics, alpha energy range 4.5 to 9 MeV. Lowest activity detectable concentration is 27 becquerel per cubic meter. Sensitivity of this cell is 0.037 CPM per becquerel per cubic meter. Photomultipliers are sensitive to vibration and mechanical shock exposure to direct light and dislocation. The next is an electrostatic correction method. Commercial product name is Radon-7. Radon and Toron are allowed in while their progeny are blocked. Radon decays to charged polonium-218. As I mentioned in the previous slide, polonium-218 collected on a silicon semiconductor detector using an electric field. In the case of Radon-7, 2200 volts are imposed. Radon concentration calculated by sniff mode, rate of decay of polonium-218 in A window, normal mode, rate to decay of polonium-218 plus polonium-214 in the A and C windows. This is an example of alpha spectrum collected on the surface of silicon semiconductor detector. This is a background, polonium-210. Polonium-218 and lead-214 are used for calculation of estimation of radon concentration. On the other hand, polonium-216 and polonium-212 are used for Toron measurement. Simultaneous independent measurement of radon and Toron can be done. Normal or sniff mode sensitivity is normal mode 13 CPM per kilobecquerel per cubic meter. Sniff mode activity 6.7 CPM per kilobecquerel per cubic meter. Intrinsic background 0.2 becquerel per cubic meter for lifetime of the instrument. It is dependent of changing humidity. This is the drawback of this technique, because positively charged radon progeny are neutralized by vapor, water in air. That's why if you use the Radon-7 in humid environment, you get a lower sensitivity. Therefore, we use a drying agent, a desiccant. Alpha track H detector. Alpha particles from the decay of radon and its progeny creates a track in the material. Tracks will be revealed through etching with hydroxide, sodium hydroxide, and potassium hydroxide. Number of tracks are proportional to radon exposure. This technique is simple to use, relatively inexpensive. Long exposure time is necessary. It is suitable for determining annual average concentrations. This track detector provides a single measure that indicates the integrated exposure. The left side shows the LR115, cellulose nitrate. The right side, CR39, polyaryl diglycol carbonate. I know Indian colleagues use this track detector. Advantage of this track detector: inexpensive, insensitive in EM, robust, and can be cut into small pieces. Their disadvantages are not reusable. Counting is time-consuming by manual counting. We can get a shorter time using commercial digital system, but it is very expensive. This slide shows the bare or open detector configuration. Here is the simplest technique. Alpha track detectors are open-faced with no filter or barrier for radon decay products. Tracks are formed by alpha particles originating from both radon and thoron and their decay products. Sensitive to radon decay product plate out on the detector surface. This technique provides assumed radon concentration, but it is not accurate. In this figure, this is a French detector. Regarding closed configuration, it is often called cup method. The filter or barrier is used to prevent the radon decay product from entering the sensitive volume of the devices. The measurement result is not affected by the presence of radon progeny in indoor air. There are several types of passive radon detectors with a cup type. I can exemplify the German passive radon detector. There is no discriminative measurement between radon and thoron. The polycarbonate film is used as a detecting material. Here is a large area glass fiber filter. which results in the large air exchange rate. And this is a plastic body. We are concerned with inhomogeneous, heterogeneous deposition in the inner wall. This figure shows a control of ventilation rate in radon monitor. Here's a radon monitor. If the radon monitor has a high ventilation rate, large ventilation rate, radon and toron, both isotopes can enter inside of the monitor. On the other hand, if the monitor has small air ventilation rate, only radon can go into the chamber, into the monitor, because the toron, half-life of toron is much shorter than radon, less than 1 minute. Toron, in this monitor, toron travels with a long time. It decays before entering the inside. So I can explain the passive radon-toron discriminating monitor. Namely, Radiate. Radiate was collaboratively developed by NIRS, this is my previous workplace, and Radosys company in Hungary. The shape is cylindrical, the inner volume is 30 milliliter, quite small. We use CR39 as a detecting material. We set 2 detectors used with different air exchange rates. Then we can eliminate the toron interference in radon measurements. The body material is electroconductive plastic. Yeah. The CR39 is placed at the bottom of monitor. And here is a holes covered with electroconductive sponge. Physical strength was enhanced by use of electroconductive sponge instead of paper filter. Maximum detectable concentration is 8,000 becquerel per kilometer. Here's the limit of detection. In the case of radon, LOD is estimated to be 3 becquerel per kilometer. In the case of toron, it is estimated to be 14 becquerel per kilometer. I will explain the charcoal adsorption method. Short-term measurements of indoor radon, optimally 1 to 7 days. Charcoal functions as a collector rather than a detector. Radon can bind to charcoal via van der Waals interaction. After radon is trapped. A proper detector measures radiation from radon and its progeny. charcoal is reusable by heating. Charcoal is also a very good absorber of water vapor, which can reduce the adsorption efficiency for radon. Here is a sample of charcoal canister. It contains activated carbon with silica gel here. And this is a cylindrical vessel. So we are moving on to the radon progeny measurement techniques. First, classification or detection. We can classify two methods: cross-counting method, the other one, spectroscopic method. Alpha particles emitted from polonium-218 and polonium-214 are counted without energy discrimination. Normally, in this technique, we use the zinc sulfide detectors, scintillation detectors. In the case of spectroscopic method, the alpha particles in specific regions are counted, where energy is discriminated according to each radionuclide. Generally, silicon semiconductor detectors are used in this method. I can show you the commercial product of radon progeny monitors. This is the active type, alpha PM. The company is the same as AlphaGrad. This is a Pylon WLX. Here's the alpha nuclear. This is a Tracer Lab BWLM plus S. Here's the Dozman Pro. All the monitors use the silicon semiconductor detector. This is a radon measurement technique, but actually, this technique used for radon gas measurement. We call two-filter method. There are two filters, upstream and downstream. This is a vessel, decay chamber. Only radon is gas, but radon progenies are solid particles. Radon progeny cannot enter inside. Only radon gas go inside. Then radon decays. And after that, radon progeny are formed and collected on a downstream filter. So we place the semiconductor detector here. We get the radon progeny alpha energy spectrum like this way. Using these counting data, we can estimate the radon concentration. Measurement of individual radon concentrations, usable filters. I can introduce membrane filters and glass fiber filters. Membrane filters are widely used. They have a higher than 99 retention of submicron particles. Aerosols are deposited on the filter surface, minimizing the adsorption of alpha particles. In the case of glass fiber filters, they are equally efficient as collectors, but most of them have small problem with self-adsorption. So the important point is that pore size and material, surface collection efficiency, which filter is the best. We use this index. Also, airflow compatibility and sampling duration. This is a typical sampling arrangement for radon progeny measurement. Components. Here are the components: open-faced filter holder and proper filter, flow meter, and vacuum pump. This is a basic sampling arrangement for radon progeny. Parameters have to be recorded. That they are sampling time, sampling flow rate, which should be calibrated. Transfer time, because polonium-218 has a very short half-life. That's about 3 minutes. So we have to hurry up to transfer from the sampling to measurement. Dr. Mehra, maybe I can stop it now. I will accept some questions. Doctor, are there any questions? I will close my talk today.
Thank you so much, sir, for your talk. Is there any question from audience side? Is there any questions? Sir, there is one question.
Yes. Oh.
So it is, what should be the typical value of unattached fraction of radon progeny in indoor environments?
Okay. Actually, in indoor environments, typical value of unattached fraction is around 0.05, just 5%. For if the air is very clean, the unattached fraction goes up to 0.2 or 0.3. Normally, the typical value is 0.5. It's fine.
Okay, thank you, sir. Thank you, sir, very much. It was really an extraordinary session for all our participants. This marks the end of first session of the day. Professor Rohit Mehra lectures will start at 1:30 p.m. IST and 6 p.m. JST. Thank you very much for your patience. We will meet on the same platform with the same Google Meet link at 1:30 p.m. Okay, thank you, everyone.
Thank you.
Okay.
Okay.
Thank you.
Thank you for the exercise. Knowledgeable lecture.
Hello. Sir, can you please repeat your question?